Good afternoon, my dear friends. I am glad to welcome you to our YouTube channel. We continue to study the theory of electrical engineering. In this lecture, we will begin get acquainted with the basic laws of electrical circuit. We will find out how many laws electrical circuits obey and list these laws. We will study in detail Kirchhoff's first law in all forms of its notation. But for now, let's remember the content of our previous lecture. We learned about the main topological concepts used in the analysis of electric circuits. Such concepts are a branch, a node, and a mesh. A branch is a part of a circuit between two nodes. A node is a junction of three or more branches. And finally, a mesh is a closed patch along the branches of the scheme. Most often, when analyzing electric circuits, we will deal with independent branches, nodes, and meshes. We will call a branch that does not contain a current source an independent one. Then its current can be any, and it is determined by the parameters of the elements of this branch and other branches. But when the branch contains a current source, its current is determined by this source and cannot take any other value. An independent node is a node that includes at least one new branch that is not part of other independent nodes. We found out that the number of independent nodes in the scheme is always one less than the total number of nodes in it. A mesh is called independent if it includes at least one new branch that is not part of other meshes. A mesh can be formed only by independent branch. The number of independent meshes in the scheme can be calculated in the number of independent branches, and the number of independent nodes is known. The concepts of nodes and meshes are used in the formulation of the basic laws of electric circuits, the study of which we begin in this lecture. We will first give a general description of these laws and then consider them in detail. Surprisingly, the theory of electric circuits is based only three basic laws. Remember, in lecture number 2 of this topic, we talk about the magic of the number 3, which we encounter in electrical engineering in completely unexpected place. We first encountered this mystical trio when we were studying the properties of the elements of electric circuits. Now this is the second meeting, but not the last. These three laws that govern processes in all electrical circuits are Kirchhoff's first and second laws, as well as the commutation law. The last law, commutation law, is the law of commutation manifests itself when an electric circuit operated in the mode of transient process. For now, we will not deal with it, so we will focus only the study of the first and two laws, Kirchhoff's laws. In 1885, in the magazine Annals of Physics, famous German physicist Gustav Robert Kirchhoff published this article. You can see a photo of this article in our slide. It was the first time laws we formulated, which were later named after him, Kirchhoff's laws. Kirchhoff's first law, which is also called the law of currents, is formulated as the algebraic sum of current acting in the node is equal to 0. Formulation of the second law, the algebraic sum of voltages in the mesh, is 0. We will discuss Kirchhoff's second law in detail in the next lecture. Now let's study the first law in detail. Kirchhoff's first law established that the algebraic sum of currents acting in a node of an electric circuit is equal to 0. In mathematical form, this equation of Kirchhoff's first law can be written as this formula. Usually, when we are talking about the algebraic sum, it means that its component can be included in the sum both with a plus sign and with a minus sign. Therefore, we need to formulate a rule according to which for each current will be determined its sign in the equation of Kirchhoff's first law. This rule can be, for example, the following. The current coming to the node, directed to the node, will be taken with a plus sign, and the outgoing current with a minus sign. Let the currents act in some node of the circuit as shown in this figure. Let's create an equation for this node according to Kirchhoff's first law. Current number 1 is directed to the node, so it must enter the equation with a plus sign. The same can be said about currents number 2 and number 4. But, as you can see, current number 3 is directed from the node. Therefore, it enters the equation with a minus sign. The algebraic sum of these four currents is 0, according to the first Kirchhoff's law. From the form of recording Kirchhoff's first law, in this form is a general case. It can be used for all electric circuits in all operating modes. But there is another form of writing Kirchhoff's first law, which is a special case of the previous one. Consider, for example, a node which include branches containing current sources, as shown in this figure. In this case, we can write the equation of Kirchhoff's first law as shown in this formula. Current source number 3 leaves the node, so its current in equation is written with a minus sign. Current source number 4 enters the node, we write its current with a plus sign. However, these two currents are known and we can transfer them to the right-hand side of the formula as it shown here. In general, this formula can be written as follows. The algebraic sum of currents in the node is equal to the algebraic sum of the currents of current sources in this node. This formulation is a special case of Kirchhoff's first law. It is clear that it can only be used if current sources are connected to the node. Please note that we moved the currents of current sources 3 and 4 to the right side with the opposite sign. Therefore, on the right side of this formula, the sign rule will change. If the current of the current source is directed to the node, then it is taken with a minus sign. And if the current of the current source is directed from the node, then it is taken with a plus sign. First law establishes that the algebraic sum of currents in a node is equal to 0. Therefore, this law is often called the law of currents. But it can be written not only for currents, but also for voltages on the elements of the branches that are connected to the node. Let's consider this possibility using the example of the circuit shown on this slide. Previously, for this node, we formulated the equation of Kirchhoff's first law for the currents of the branches approaching the node. I1 plus I2 minus I3 and plus I4 is equal to 0. But let's remember that from lecture number 3 of this topic, we know the relationship between voltages and currents of passive elements. The relationships are summarized in this table. The relations allow in particular to express the current of each passive element in terms of the voltage on it. So, this is a possibility to write the equation of Kirchhoff's first law not through current, but through voltages acting on the elements. Consider the equation of Kirchhoff's first law considering currents. Current I1, according to this scheme, acts in the resistor R1. From this table we can see that the current of a resistor is related to its voltages by the equation IR is equal G, this is a conductance of this resistor, times UR. In our case, we can write that I1 in resistor number 1 is equal 1 over R times UR. For the capacitor C2, we have I2 is equal C2 times derivative du2 with respect to dt. And for inductor L3, we can write I3 is equal 1 over L3 times integral from u3 with respect to dt. And finally, for inductor L4, we can write that I4 is equal 1 over L4 times integral from u4 with respect to dt. Thus, the equation of Kirchhoff's first law for our node can be written as shown here. Note that this equation, unlike the equation for currents, is an integral differential equation. Our lecture has become to an end, and now is a time for some conclusions. First of all, today we know that all electric circuits obey only three basic laws. This is Kirchhoff's first and Kirchhoff's second laws and the law of commutation. All other independencies are consequence of these three basic laws. Kirchhoff's laws are universal. That means that can be used for all types of electric circuits in all modes of its operation. There are two formulations of Kirchhoff's first law. First formulation is algebraic sum of current in node is zero. This is basic formulation, and this formulation can be used in all cases. Formulation in the form algebraic sum of current in node is equal to algebraic sum currents of current sources for this node can be obtained from the basic formula, and it's commonly used in equations for calculated electric circuit that contains current sources. We know that the equations according Kirchhoff's first law can also be written not only in terms of currents, but also in terms of voltages on the elements. In this case, unfortunately, they are integral differential equations. And I need to say that in the vast majority of cases, the number of unknown currents, that is a number of independent branches in the circuit, is greater than the number of independent nodes. Therefore, only the equations according to Kirchhoff's first law are not enough to calculate these currents. And in our next lecture, we will get to know about Kirchhoff's second law in detail. Thank you very much for your attention. Have a nice day. Goodbye, my dear friends.